Okay.
Yes, perfect.
Okay, so, hello everyone. So my talk will be about two-photon selection rules in Rydberg state excitation. So this was a joint work with me, Kaspars Mičulis, who will be talking tomorrow, and Nikolai Bezuglov, who is professor at St. Petersburg State University. Okay, so let's start with the motivation. So why would anyone want to study Rydberg states? Well, first of all, Rydberg states are very exciting as they have several interesting applications in sensing, quantum optics, and quantum information. So for example, in sensing, you can utilize the fact that Rydberg states are extremely sensitive to external fields. The same applies for applications in quantum optics, and in quantum information, you can use both this very high sensitivity to external fields, and also the fact that Rydberg states in ensembles exhibit interesting collective effects such as dipole blockade. Now, when you want to do things like this, what you first need is a method that allows you to prepare atoms in your desired Rydberg state, or even a superposition of Rydberg states. And this is the point where our research comes in, because we are trying to develop a method to control selection rules, which define the range available for the range of levels available for excitation. And why was there hyperfine interaction mentioned in the title? It's because hyperfine interactions are present whenever nuclear spin is non-zero, and most naturally occurring isotopes of element atomic particles have non-zero nuclear spin. So they all exhibit to some extent hyperfine splitting. Yeah, and this is courtesy to Latvian Science Council grant. So why is taking into account hyperfine splitting important? Because without hyperfine splitting, of course, selective excitation in 3 or more step excitation schemes is straightforward. Because first of all, if you have more than one level in the ground state, you can polarize the ground level using optical pumping, for example. And then, since using polarized light allows you selective excitation of Zeeman sublevels, then you can selectively excite basically whatever you want. However, when there is hyperfine interaction present, unfortunately, things are not so simple, because it introduces both splitting and mixing between Zeeman sublevels, and so selectivity is much worse. For example, this is the example of atomic sodium, where you have ground level hyperfine splitting of nearly 2 gigahertz. And so you will always start with atoms in a well-defined hyperfine level. Basically, you need to have very strong lasers to simultaneously excite both hyperfine components of the ground state. However, in the first excited state, which would be 3p 1/2 or 3/2, you have some considerable hyperfine splitting, and then for highly excited states, the hyperfine splitting becomes very small or almost negligible. Of course, one can think of a few examples where in such excitation scheme you can implement selective excitation of the Rydberg state. Because, for example, you can use excitation from f = 1 state to f = 0 state in an intermediate state, and then you, according to a single transition electrodipole selection rule, you can only excite F equals 1 states in the Rydberg state. So some selectivity is possible in this case, but only if you use weak lasers, because if you use stronger lasers, which would allow you to have more population in your final state, you inadvertently will excite also some of the other hyperfine components in the intermediate state. So what we did is, first we analyzed the excitation scheme using Morse-Short transform, which decomposes the excitation scheme into bright states, dark states, and what we called chameleon states, which may in some cases interact with laser light, but are usually not populated in any way. However, in this situation, it's almost clear that even if there is a hyperfine structure, selectivity is still there. It's just very bad. Sorry, was there a question? Oh, okay, so there is this hyperfine splitting. Okay, so here is in the ground state, of course, there is this 2 GHz splitting, which is shown. In the intermediate state, we have shown bright states and dark states, and plus hyperfine splitting, because it's very small in this comparison. And of course, the final state is almost degenerate. So in order to reduce mixing between excited intermediate bright levels, we proposed to use blocking laser, which would block excitation to travel, block excitation from traveling between those two bright states. And in conclusion, I will show examples. The first example is excitation via the intermediate 3p3/2 level to highly excited NS 1/2 level. So this is the excitation scheme. And when we calculate how the excitation is transferred from the ground state F equals 2 to the final state NS, so we see that both hyperfine components of the Rydberg state are populated a bit differently. It of course varies depending on the two-photon tuning and on laser Rabi frequencies and all those factors. However, this is somewhat selective excitation. You wouldn't call this controllable excitation, because as you can see, selectivity is virtually always there in some form or another. Now let's consider another example, which is excitation involving 3p1/2 as intermediate state. In this situation, you normally would not expect any selectivity, because as you can clearly see from the excitation scheme, the selection rules allow all the hyperfine components to be excited if your lasers are sufficiently strong. However, now in this scheme, if you introduce blocking laser, then selectivity appears. So the first column is pictures in simulations without a blocking laser, and as you can see, selectivity is non-existent basically, apart from very small differences in populations. However, as you increase the blocking laser intensity, the difference in Rydberg state hyperfine component populations increase. So in this situation, we can say that we can control how selective our excitation scheme is. So basically, if you do the math, here you see that the selectivity corresponds to two-photon transition where total atomic angular momentum does not change. And yeah, this is our main result, which will be published in upcoming months. And we hope that shortly thereafter we'll carry out experimental investigation where we expect to confirm this theoretical result. So thank you for your attention, and I'm open for questions.
Thank you. Please, questions? I have a question to Artūrs. In your slides, you showed the comb-like structure. Yes, in this slide. Where does this structure come from? And it is in some slides, but in other slides is not present. Or in some plots it is present and in other is not present.
No, we suspect that this should be due to numerical instabilities in our simulations mainly. So this is not really a comb-like structure.
So this is not a natural line with effects. It's numerical instability.
Yeah.
Okay, thank you. Some more questions?